Welcome to this lecture series in real analysis. In this lecture, we look at the very important notion of Cauchy sequences, and let us recall what we need. So we will need to know what is a sequence, what is a subsequence, and especially what are convergent sequences. So these two notions apply to not necessarily to real numbers, but when we say convergent sequence, at least for this lecture series, we mean a real sequence which is convergent. Okay, and we need to know this fact, which is called the Bolzano-Weierstrass property, which is that every bounded sequence of real numbers has a convergent subsequence. How did we prove it? First, we extracted a monotone sequence out of a bounded sequence, and once you have a bounded monotone sequence, then it converges, and therefore every bounded sequence has a convergent subsequence. All right. So here are some problems for practice. And now let us get started. So we will define first what is a Cauchy sequence. So a sequence of real numbers is called a Cauchy sequence if for all epsilon greater than 0, there exists a natural number n such that the distance between the mth term in the sequence and the nth term in the sequence is at most epsilon whenever m and n are at least capital N. So what is it trying to say? It's trying to say that you fix some tolerance region, tolerance level, then beyond a certain point, any two elements of the sequence are same up to a tolerance of epsilon. Any two elements of the sequence beyond that point are kind of same up to a tolerance of epsilon. That sounds like a very strong property, right? If you try to visualize what this is saying, you will see that, there is some epsilon band such that beyond a certain point, any two elements of the sequence are within that epsilon band. So I'm trying to depict the graph of the sequence. Anyway, so you should maybe pause for a moment and think about what this is trying to say. I don't want to say too much about the definition because it's not intuitively very hard to digest this notion. All right, but to understand things better, we will fully characterize Cauchy sequences in this lecture itself. So first we will show this simple property that every Cauchy sequence is bounded. Right? Why is this? So start with a Cauchy sequence. And intuitively, why will this sequence be bounded? Well, beyond a certain point, all the elements of the sequence are within epsilon of each other. So they are kind of controlled beyond a certain point. But before that certain point, you can just take the maximum of the maximum of the absolute values of all the elements. And that will serve as a uniform control on the size of every element of the sequence. So that is essentially the proof, but let us write it down in full detail. So since it is a Cauchy sequence, there is some n. So let n be a natural number such that this happens, xm minus xn is less than 1 in the absolute value whenever. So why does this happen? Well, here this statement was true for all epsilon. So we just chose epsilon as equal to 1. And immediately by definition of a Cauchy sequence, we get this. All right, so we have that. So therefore, in particular, we have this happens whenever n is at least capital N. So what happened here? This was true whenever m and n were at least capital N. So we just chose little m as capital N and left little n dummy. Okay. So therefore, just by straightforward triangle inequality, we see that this is the case. Right, and lastly, and that concludes that the sequence xn is bounded. So why does the last thing happen? Well, if little n is exceeding or is at least capital N, then this bound works simply because this is sitting over here. And if little n is smaller than capital N, then one of them dominates this guy. So it's a very simple thing. And now towards examples of a Cauchy sequence, just note that every convergent sequence is Cauchy. So let's demonstrate this also. Why is every convergent sequence Cauchy? So fix a convergent sequence. And we want to show that it is a Cauchy sequence. Let's argue informally first. So once you have a convergent sequence, it is becoming closer and closer to a point, let's say little x. So there is some real number little x, such that all the points of the sequence come closer and closer to this. And if ultimately they are close to x, ultimately they are close to each other. And that's kind of what Cauchy sequences are about. Ultimately, they are close to each other. So that's a very informal reasoning. Let's write down a formal proof. So say x is the limit of this sequence. All right. So then by definition of convergence, so fix some epsilon greater than 0. And once we have done that, we just need to show this part. To establish that the sequence is Cauchy, we need to establish that much. All right, now by definition of convergence, we know that there is some capital N such that this is at most epsilon by 2. Sorry, what am I writing? Xn minus x in the absolute value is less than epsilon by 2 for all little n at least capital N. Right? Convergence immediately gives us this. Okay. Therefore, this is at most epsilon by 2 plus epsilon by 2 whenever little m and little n are at least capital N. So what happened? There is some big enough n such that this is true. So we just used it 2 times. Once we used the index m, the other time we used the index n. So we just kind of use this 2 times. And this we can, let me write this just somewhat differently. Right? And now by triangle inequality, we have xn minus xm is at most epsilon whenever, there is no space. Right. So just give me 1 second. Yeah. So this thing dominates that thing. That is by triangle inequality, and it is dominated by epsilon, and therefore this is at most that whenever little m and little n are at least capital N. And therefore the sequence is Cauchy, because this is exactly what we wanted to deduce. Alright, so every convergent sequence is Cauchy, and therefore there are ample examples of Cauchy sequences. Okay. Now the point of this lecture is to actually show the reverse. We want to show that every Cauchy sequence is convergent. And therefore, the notion of a Cauchy sequence is actually not a new notion. Right? It is the same as the notion of a convergent sequence, even though the definition is somewhat different. And it's actually very useful to have this, to have this equivalence, that Cauchy sequences are same as convergent sequences. It is somehow easier at times to establish that a given sequence is Cauchy than directly using the definition of convergence. And we will see examples of it, maybe not in this lecture, but ultimately we will see examples where checking the Cauchy condition or using some deduction out of the notion of Cauchy sequence helps us establish convergence of a sequence, which is not immediately or obviously clear just by straightforward definition of a convergent sequence. Okay. So suppose now we have, our goal is now to show that every Cauchy sequence converges, and towards that we will have certain lemmas. So fix a Cauchy sequence, and we will show that if there is a convergent subsequence of this guy, then the sequence itself converges. So if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself converges. This is what we will do first. This is what we will do first. Okay. So why is that? Again, let me try to first argue informally. So we have some Cauchy sequence. It has a convergent subsequence, which for the moment think of as a constant sequence. A convergent subsequence or a convergent sequence in general can be informally thought of as a constant sequence because it ultimately just becomes closer and closer to a fixed point. So think of, suppose this houses a constant subsequence rather than a convergent subsequence. Let us more strongly assume that this guy has a constant subsequence in it. Okay, so if this same number appears frequently in the sequence, which is to say that there is a constant, that this sequence has a constant subsequence. So there is some number x which appears frequently in the sequence. Now, by the Cauchy condition, ultimately or beyond a certain time, any two elements of the sequence are close, and hence in particular, any element of the sequence is close to this number. And that is what establishes the convergence of the Cauchy sequence. So this informal reasoning is what we will make precise. Okay. So start with a convergent subsequence. Right? We fix a convergent subsequence and say x is the limit of this guy. Okay. We will, of course, conclude that the Cauchy sequence itself converges to x. All right. So fix epsilon greater than 0. And we want to show that, or we will show that. What? This is less than epsilon ultimately. Right? This will establish convergence. This will in fact establish that the sequence converges to the point x. Okay, so this is our goal. And now, by the blue thing, let's call the blue thing as star. By a star, there is some capital K such that this is at most epsilon by 2. So we have already fixed some epsilon greater than 0, and therefore by the definition of convergence, this expression over here, this thing, is at most epsilon by 2 or strictly less than epsilon by 2 whenever little k is at least capital K. Okay. All right. And by the fact that the sequence is Cauchy, since this is a Cauchy sequence, there is some capital N such that this is also less than epsilon by 2 whenever this is the case. Okay. So now let K prime be large enough such that this exceeds N or is at least N whenever K is at least K prime. Such a K prime must exist because N1, N2, N3 is a strictly increasing sequence of natural numbers. Such a K prime exists. Okay. And thus therefore, if K is at least both K and K prime, we have x m minus x n k is less than epsilon by 2, and so whenever, here I would write whenever m is at least capital N, and so let me justify the statement. So whenever K is greater than both of, or is at least both of them, meaning it is at least the maximum of these two things, this happens. Why? Because if K is at least that much, this is at least that much, as written over here, and therefore if you just use this statement, we have little m and this guy both at least capital N, and therefore their difference in the absolute value is at most epsilon by 2. So as soon as this happens, we can write this. And this automatically is true because if K is at least capital K, then that's exactly what we've written here, that this happens. So when K is at least the maximum of these two integers, this statement happens, and therefore this summation is less than epsilon by 2 plus epsilon by 2 whenever m is at least capital N. So what I'm trying to say is that if this is the case, then that is the case. But now apply triangle inequality. So if you apply triangle inequality, let me just write that here itself. This term will dominate xm minus x, right? And this is epsilon. So by triangle inequality, what we will get is this is at most epsilon whenever this is the case, and therefore the sequence itself converges to the point x, because this is exactly what we wanted to establish. We wanted to prove this, and that's what this is. Okay, so all of these deductions are pretty simple, although they might in print look somewhat complicated. Okay, and now finally, we are in a position to show that every Cauchy sequence converges. We will just put together the facts that we know. So let me formally write down the proof, but it's a very simple deduction from given what we know. So let Xn be a Cauchy sequence. Okay, we have a Cauchy sequence. Therefore, it is bounded. And now by the Bolzano-Weierstrass property, it has a convergent subsequence. Okay, it has a convergent subsequence. But now, what we see is that we have a Cauchy sequence with a convergent subsequence. We started with the Cauchy sequence. We showed that it has a convergent subsequence. But by what we proved in a few slides ago, that this implies, well, only the first statement and this last statement together, they imply that the sequence is convergent. Right? Because if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself is a convergent sequence. So we have already shown that every convergent sequence is Cauchy. Now we showed that every Cauchy sequence is convergent. And hence the notion of a Cauchy sequence is precisely the same as that of a convergent sequence, which is what we have recorded over here. All right, so next lecture we will see an application of this concept. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.